Hello, everyone. My name is Aziz Mahaisin, and I'm an associate professor at the University of Central Florida. I apologize for not being able to make it this time for other commitments. And today I will be presenting our work, subgraph-based adversarial examples against graph-based IoT malware detection systems. This work is joint work with my PhD students, Ahmed Abu Snena, Hisham Al-Asmari, Muhammad Abu Hamad, and my collaborators, Saeed Salim and Dehan Young. And this work is supported by NSF, NRF, and Cyber Florida. So this is the outline of the presentation. We start with the introduction of Internet of Things and IoT malware, dataset, and baseline model utilized through our proposed adversarial method, and ending with the discussion and conclusion. And so the Internet of Things devices are rapidly growing and are equipped with different software. In November 2018, Ericsson Mobility Report showed that the expected cellular IoT connections will increase to 400% within 6 years, especially in Northeast Asia. Now, similarly, the number of connected IoT devices are expected to rapidly grow in the following years, according to statistics by HIS 2015 report. Now, currently, there is more than 26 billion connected IoT devices, with a global IoT market worth about 1.7 trillion United States dollars. However, with the increase of IoT devices and connections worldwide, IoT malware growth highly increased. Here are some examples of rapid growth of the IoT malware threats in the years 2018-2019. This is due to the increased software vulnerabilities along with the increase of IoT devices. This chart shows you the number of malware samples for IoT devices collected by Kaspersky Labs. The number of IoT malicious samples collected in 2018 is about 40 times more than that of the samples collected in 2016. With the increased threat of IoT malware, customers choose IoT devices security as the main issue, stopping them from adopting IoT technologies. Recently, various deep learning-based IoT malware detection systems were proposed in the academic literature, achieving up to 99.9% accuracy. Similarly, applications of adversarial learning came to light by applying minimal perturbations to the input data to cause misclassification. Our goal in this study is to investigate the robustness of deep learning systems against practical adversarial examples. The practical adversarial examples are samples generated from original IoT malware with the same malicious functionality and classified as benign. In this study, we focus on one of the state-of-the-art approaches, the control flow-based IoT malware detection systems. And by the way, the original work that we will base our study on was proposed in CSoNET 2018, the last year's version, which was held in Shanghai. So the contribution of the work is as follows. First, we investigate the robustness of the control flow graph-based malware detection system against practical adversarial examples. Then we propose SGM, a black box adversarial approach to generate practical adversarial examples with a reduced overhead and size. Next, we will talk about the dataset and feature extraction processes that we have followed in this work. Our dataset consists of 3,000 IoT malware samples collecting from OpenWRT and 5,670 IoT malware samples also gathered from IoT bot. These malware samples consist of 3 different malicious families as shown in this table. Afterwards, we extract the control flow graph of the samples using Radar 2, which is a reverse engineering framework. Then we extract 23 algorithmic features from the graph, including degree, betweenness and closeness centralities, shortest path, density, and number of edges and nodes. Let's describe our baseline model. Our first baseline model is a CNN. And so the CNN consists of 4 CNN layers, conventional layers, with ReLU activation function. As we can see, there is 3 basic blocks. The first block consists of 2 consequential convolutional layers followed by a max pooling and dropout. The second block is similar to the first block, although applied on the output of the first block. However, the third block starts with flattening operation, followed by a dense layer of size 512 and dropout operation. And lastly, dense layer with a softmax activation function. We achieved through this baseline model a malware detection accuracy rate of 98.96% and a classification rate of 98.09%. The second baseline model is a deep neural network, and this deep neural network, or DNN, consists of 6 fully connected layers with below activation function. With a 2 dropout operations to prevent overfitting, we achieved a malware detection accuracy rate of 98.67% and a classification rate of 97.57%. Now let's get into the GIA approach, which was proposed earlier. We examined the robustness of CFG-based IoT malware detection systems over adversarial examples generated using the GIA approach. The basic idea of GIA is to connect two graphs, original and selected graph or adversarial graph, the nodes to be added on the original graph, to generate the adversarial example. For now, let's combine the script of the original graph shown herein. We then select a script of a selected sample to be added. The connection must maintain the functionality and the practicality of the original sample in the above part of the graph, of the figure here, leading to potential practical adversarial example. Here is the combined script with a simple combination. The blue area represents the original sample script, and the red area represents the selected sample script. We define a condition variable to ensure that the functionality is intact. Now let's understand what is happening on the corresponding control flow graphs. This graph represents the CFG corresponding to the original sample. And so the CFG corresponding to the selected sample also here in red. This is the combined graph resulting from the connection induced in SGIA of the original and the selected sample. As we can see here, both graphs still exist internally with a shared entry and exit point. To evaluate GIA, we vary the selected samples by the number of nodes referred to as the size of the graph. This table shows the malware to benign misclassification rate and a cracking time of the adversarial examples. We vary the size of the benign selected samples from 10 to about 1,000. The misclassification rate, as we can see here, increases with the increase of the selected sample size, which is expected. The reason is that the feature extraction process is highly affected by the embedded graph. We could achieve a misclassification rate of 99.64% using a benign selected sample of size 23 nodes. However, the crafting time also significantly increased with the increase of the selected sample size. We observe that the same behavior on the benign to malware classification process also exists, achieving a misclassification rate of up to 60%. For the classification model similar to the detection process, we vary the size of the selected samples. This table shows the non-targeted misclassification rate for each family and the crafting time of the adversarial examples. We observe the same behavior from the detection process, achieving a misclassification rate of up to 10% from the benign to any malicious family. Similarly, this table shows the targeted misclassification rate over CNN and DNN classification models that we described earlier. We achieved a targeted misclassification rate of up to 100% for benign to all malicious families. However, injecting a graph of size 1,075 nodes, roughly 1,000 nodes, is quite expensive. What if we could preserve the performance and reduce the injection size, which we pursue next? To solve this issue, we propose our main contribution, which is the subgraph embedding, or SGIA. And so the key idea here that we try to achieve with this approach is to focus on reducing the adversarial overhead required to cause misclassification. And so first, we start with disassembling the samples and extract the corresponding CFG graphs. Then we use an off-the-shelf algorithm called CORC, which is a greedy algorithm to search for the target pattern set to extract discriminative subgraph patterns from each malware family. Then, after extracting the discriminative subgraph, we then embed the subgraph with least size into the original graph. If the generated graph misclassifies the classifier, return the generated sample. If not, find the next least subgraph and repeat until you achieve the criteria of misclassification. If all extracted samples fail to cause misclassification, then return the original graph. And so to evaluate SGIA, we started with detection models. We were able to misclassify all malware samples as benign with an average subgraph size of 6.8 nodes, which is amazing. However, it is not efficient to misclassify the benign samples into malware using SGIA, as we achieve only a misclassification rate of as low as 22.22% of an accuracy, which is the downside of the approach. However, keep in mind that oftentimes it is sufficient to demonstrate the operation of the system of actually disguising malware samples into benign samples, which is in security settings is the ideal requirement for a system to misclassify, which we achieve here with 100% accuracy. Similarly, we evaluated SGIA on non-target misclassification capabilities. And so for the CNN-based model, the left figure is the misclassification rate, where columns represent the original samples class and rows represent the connected subgraph class, whereas the right figure shows the average nodes overhead needed to cause misclassification. Now, this is also the result for the DNN model. We achieved a non-targeted misclassification rate of almost 100% from all malicious families using benign subgraph of size of as low as 6 nodes. For the target misclassification, a successful targeted attack occurs when the sample misclassifies as the class of the injected subgraph. And so for CNN-based models, SGIA successfully misclassifies almost all malicious samples to benign with an overhead of up to 20.4 nodes. Similarly, we achieved results for the DNN-based model. As observed, SGIA reduces the adversarial example overhead and the injected size while maintaining the adversarial performance of the generated sample. So finally, we will conclude our presentation with a discussion and concluding remarks. And so GIA actually generated adversarial examples that are practical, preserving the functionality and practicality of the original sample. However, to achieve a good misclassification rate, high injection size is required, resulting in an easy-to-detect adversarial example. However, SGIA, which is the main contribution of this work, is an approach that preserves the functionality and performance of the generated adversarial examples with reduced injection size and overhead. In comparison to GIA, making it harder to be detected as well. And so, on the downside, however, this approach requires an oracle to the targeted model and a high computational time and power. So, in conclusion, the main issue with deep learning-based malware detectors is that the extracted shallow features are used, making it possible to manipulate the sample while preserving the functionality and practicality, even when a small perturbation is applied. In order to increase the robustness of the model, deep, robust features are required. As a future work, we are interested in investigating deep features that are hard to manipulate while preserving the practicality of the samples. And we are also interested in proposing practical methods to distinguish normal and adversarial examples against GIA and SGIA. Thank you very much for listening to my talk, and I again apologize for not being able to make it, nor being able to send my student to present this work in time. However, I'll be very glad to answer any question that you have. If so, please email me at mohaisen@cs.ucf.edu. That is MOHAISEN. Thank you very much.